even deeper. So you might remember earlier on that I mentioned HKL. What does this HKL mean? Why it is important? Why do we speak about this? So that's the idea now. Now, once we know the unit cell, it doesn't matter what is the shape or size of the unit cell now. This concept, what you will learn here, relates to the unit cell itself. And we discuss or make a definition about, again, an imaginary thing. This doesn't really exist, but we think that it exists. And we call it a lattice plane. So what we do now, we think that, okay, we have the box, we have the unit cell, we have the box. We now start thinking that there are planes going through the unit cell, like that. And we call these lattice planes. And now each individual that's kind of a plane, we will have also a name for it. And the individual plane we name as HKL. And the HKL is called the Miller index of that particular plane. Why this is important becomes more evident later on. So the point is it's possible to describe diffraction as a reflection. Remember, the phenomenon is diffraction, but what comes out from there is reflection. And now we have to, in a sense, in order to, if we can measure the orientation where the reflection is coming, we know we should be able to determine the plane, consider that as a mirror, imaginary mirror where the reflection is happening. And now this mirror, which makes this thing out, is called the HKL, and the Miller index is the general definition. And the orientation relative to lattice is defined by a Miller index with the value of HKL. So the HKL, the numbers, it's a set of numbers, tells what plane it is. So we can have these planes, and each plane has a name. So we can know that, okay, this plane is this one, this plane is this one, and so on. And it will soon be relevant for you why we need this. So the idea is that the lattice planes are parallel stacks, and each point the lattice lie in the stack. So the point is that we take like a slicing of the box into a planes. And the idea of the HKL is that such a stack can be determined by examining a plane which lies nearest to the origin without throwing past of it. So there will be a picture soon. So if the plane intercept A, B, and C in the unit cell axis, it will be defined by 1 over H, 1 over K, and 1 over L. And then we take that, this is a fraction, but the fractions are very difficult to handle. So at twist, we turn it upside down. So the idea is that the point, this is the case. So here we have a unit cell now. And now this, in this case, this blue is the imaginary plane, which slices through the A, B, and C axis. And now it slices that in the position 3 here, and the position 3 here, and the position 2 here now. It means that now the indicators are, because it's always 1 over something, so 1 over 3, 1 over 3, 1 over 2, but this would be really difficult to handle, so we flip it over. So this number, the fractions will become into the numbers. So that will be 3, 3, and 2. So this is now the name of this one plane. And this is unique for that unit cell. We don't have to know the length of A, B, and C again, because this relates to the axis itself. So it is just where the position where it crosses the unit cell. So here, this is now like 1, 2, 3, 4. This is one axis. So it cuts then in here. Here, there's 1, 2, 3, 4 is here. That's the one. 1 is here. So it cuts that in 3. And here, 1, 2, 3, 4. And it cuts that in 2. So that we get the fractions of the unit cell axis, and then we just flip it over. And then the plane, name of this plane is this one. Now remember, I told you that the diffraction can be considered to happen from a plane. And now, if that happens, this one plane now contains certain points reflect from that. And if that is true, we will see that as a reflection. We see that as a point like this. So that could be a reflection from this plane through 332. But that's the Miller index. That's the H scale. This is the lattice planes. The Millerites are reciprocals on the intercepts of H and so on, like I described there. The left-hand side is this. And now, if you look here, different here, now the crossings are different. So this plane now, which goes like that direction, is called 1, 3, 4. So what we can do and what happens is we have a combination of all the numbers. So they start from 0, 0, 0, which is nothing. But then we can have 0, 0, 1, 0, 0, 2, 0, 0, 3, and so on, depending on how many times we slice the axis. And you notice this kind of a thing here. This is the same plane. It slices there, there, there. They're the same direction planes. And the idea is that the more of these planes you make inside a unit cell, the shorter is the distance. And now remember the Bragg's law, where we have the D. So the Bragg's law D is the separation of these planes. That's why we need this. And that is why we need these planes also, because then we can define with these planes, we can define the distance where the diffraction happens. So here is the definition for this. Now, let's start doing this thing. Again, in a similar way of this, let's start sliding. So look, so now this is two-dimensional. In 3 dimensions, it gets really complicated. Luckily, we have the computer which is doing this. We don't have to worry about this. But the point in there is that, okay, now we have A and C axis. B is on that direction. And we slice. We now draw a line here, which is the plane, which cuts C in 1/2 and A in 2/3. Let's see what happens. Now, A is 2/3. B is infinitive because it goes along it. So it doesn't cut anything. And then C is 1/2. Now we take a reciprocals for these. So this one turns 2/3. This becomes 0. And this becomes 2 or a 1. And now the idea, you said they are still fractional numbers. And they have to be integer numbers. So what we do, we take the common denominator, which is 1.5. So we multiply all these things by 2. So by multiplying this here, we get 3, 0, 4. So the name of this plane is 3, 0, 4. Now, this is not the only one. We can draw the same plane. So if you do the same, and you can do this if you like at home, do the same thing. So now 1/4, 1/4. In here it's 1. And then they're all the same. They're the same plane. We can have a stack of planes in there. Depending on how many times they cross over the axis, that many planes there will be. So that's the idea. That's the same plane. Now, there is a mathematical calculation for this. You can easily do that for all of them if you like. But that's the idea. That's the name of this plane. Now, what happens? Okay, let's draw a new here, which says 1/4 C and 1/3 of A. So we just draw it on top of it. So let's do the calculation in here. Now 1/3 reciprocals 1/4 reciprocals 3/1, 0, 4/1. Now it's the same. Of course it's the same because we draw over it. And in this way we can do this definitions as we like. Now, what is this? Now, this is the same as there because we now cut the A in half, but now it goes along A and B. It doesn't cut them there. They are infinitive. We take a reciprocal. It's 2/1, 0, 0, and then the Miller index of that is 2, 0, 0. So this plane now here is 2, 0, 0. So in this way, we can develop all possible planes that you can draw in a unit cell. Luckily, again, this is purely mathematical procedure with the computer does automatically for us. So we don't have to worry about this. But that's the concept. So, and later will be relevant why this is important. Why do we need this information? So that's the same thing in here. We can do this more, so we can actually have this kind of a plane. And now when we do this plane here now, that plane will be 1, 0, 2. So here is 3, 0, 2. So we can have this. You can see now all of them are drawn in the same unit cell, but they're all individual. It's like a separate, now I draw all of them there, but they all behave like a separate set of planes, like individual. Now, two-dimensional illustrations. Well, we will look for the planes where this is 0. We only look for HKL. The plane is not intercepting the C, so L is 0. And then the idea will look, okay, this one here would be 1, 3. That kind of a thing, that is points. Here it would be 1, 2, 0. So that would be like a 1, 3, 0, 2, 1, 0, and so on. Here you can see there are more planes. 3, 4. This would be 4, 3, 0. And the point in there is that the higher is the number, the more planes you see. In the other way around, the separation of these, the D, is bigger when these numbers are smaller. And the bigger are this number, the smaller is the gap between these lines. You can see here, this is the shortest, the smallest one at the long difference, the same in here and the same in here. And the point in principle, the lattice is always the same. The lattice itself is the same, but the planes, how you draw it there, are different. The bigger is the number, the more thicker or more amount of these lines are, or planes are there. That's the same idea. Okay, like this, you can make a definition for these things. They're all with the same lattice, different planes. So this is also not very relevant. I will skip it very briefly, but the point in there, normally the HKL, you can make a combination of these. You can present the direction and present a lattice plane. This is the normal, or this is the family of planes and so on. So here's one example of this, this kind of a bracket, 1, 0, 0, means all of them. So if this one is the same as this one, this is the same as this one, and so on and so on and so on. So in dumb systems, like in cubic system, the individual planes like this plane and a similar plane in this direction is the same. Because it's so highly symmetric, so symmetrical. So that is the reason for the Miller-Innes planes. They also relate to the symmetry of the unit cell, the lattice. But again, we don't have to worry about this because the computer knows this. 100 years ago, you had to separate them by hand, by calculations. Now we don't have to. So here, let's have some quick animations and drawings. So unit cell is there, X, Y, and Z, A, B, C, and now A is here, B is there, and C is there. Let's see what happens. So we draw this. So what does happen in here? So the point is it intercepts only one, which is now a B here. It intercepts, it's in 1, but doesn't intercept A or C, so it's 0, 1, 0. What happens if we now take this one, consider that as a cube, what is now on this side? So it now goes through in a different way. The orientation is the same as there, but it cuts the different. It now cuts the A, but not the B and C, so it's 1, 0, 0. They are two different planes. Now, what is this? So this now cuts the C, but not A and B, so it's 0, 0, 1. And now, this is like a 1/2 of it. We have the other side also. Let's see. Now what we have to do is that we have to look then on that side, and now we have to think about that this is now the same plane as this, but from the other unit cell, then this will be easily defined, or it is defined as a negative of this. This is -1, because it cuts that on the minus side. And then in here, if we look, another thing, that is the same, we put it here, then it's a reverse of this, so it's 0, 0, -1. And then finally, of course, we can have one thing missing there, and that the idea, that would be, of course, the counterpart of that. So that is the idea. That defines the unit cell. And this is now interesting that if we are looking for these things, so 0, 0, 1 and 0, 1, 0 and so on in the negative form, that will form the unit cell. Because these are along the unit cell axis. This is the unit cell which is created now by the planes of these things. Because by definition, they cut always the axis in one point. And it's at the end. But what we want to do is, of course, to draw, these are all needed, but we have to draw also these lines, or sorry, the planes inside the unit cell. So let's do the same thing now. Now, what is this? Now it cuts here, it cuts the different things in here. So it goes here in one, it goes along that one, it cuts in there, in this one. We have to move that in this direction. So then this plane would be 0, minus 1, 0. And this is a simple one. Now when you start imagining, I will go very fast these things because it's difficult to memorize all these rules. But the idea is that in this way you can build up and see different, you can see that the idea in there is that you slice the unit cell in a different directions. So now this is the same, but now it's 1, 0, 1. And we always, now the number is very small, it's only 1. It doesn't cut more. So let's see what happens if we take this kind of a thing. Now, it's the same now. In here, it's minus 1, 0, 1. Now you can see that they can be this direction, or they can be that direction, or this direction. That this direction depends on the Miller and index numbers, meaning the direction how they slice the unit cell. And in here, the same thing again now, but now we go on the other direction. So now 0, 1, 1. So it cuts two of these axes in one, and it doesn't go cut the one at all, so it's 0. Then there will be more complex things going forward like this. This is a new plane. And now this plane is 1, 1, 1. So it cuts all the angles at 1. So there's an origin, so 1, 1, and 1. This plane is 1, 1, 1. And the point, this is the same plane. And there is a plane, there is a plane. And now these planes, which is like a negative for that, but only on one direction, is 1, 1, minus 1. And now if you try to imagine all these possibilities, your brain will get stuck. It will be virtually impossible to visualize all these possible connections when the numbers get big. And these are the very simple ones, the idea is. So here are examples here where we have some things, but look what happens in here. So we divide x, y, and z, or a, b, and c in these parts. So the words 0, 3, 0 is this one, but there will be 3 of them. This is 0, 4, 0. Now 1, 2, 3. So 1, 2, 3, and it makes one slice. So 1, 2, 3, 4 things, because this is slices the unit cell axis into 4 parts. And that is 0, 0, 0, 4, 0. And that is the same thing, and this is the same thing. And now the blue ones, or the big ones, are exactly 1/2 of it. Because now blue one, or the pink ones, will slice it only twice, and then this is 0, 2, 0. So the point is that some of the planes overlap. So this one here, the yellow one is unique, but in here 2 and 4 overlap. So of course the planes can overlap because we have a multiplicity here in this case. So every second of these will be the same, and these ones will be unique. Okay, let's see even more examples of these. Let's happen with this one now. And now this is now 0, 0, 4 because it splits now the x or c axis into 4 pieces. And now it just quite quickly go through these things. And you can see just the different variations of these things. So this kind of a thing, that kind of a thing, this kind of a thing. This is also a plane, that kind of a thing. So you can see that we have absolutely nearly indefinite possibilities for this. But this is not true. We can do this, but there is a practical limit. And we will soon see what is the practical limit. So we can also define the Miller index by the vector definition. And the vector definition is D. This is actually the separation of these planes, or the point with there. But now we do the reciprocal. Somebody was asking me the first time about the reciprocal lattice. So what is the reciprocal point? What is the reciprocal lattice for? So the reciprocal lattice is simply a mathematical formulation of the Miller index plane. So each individual Miller index plane, like this here now, because that's the distance dHKL. Now, when we do this reciprocal lattice transformation, it turns to a point. And that's nothing more. So why this is important comes out later, because it's much more mathematically easy. But the point is this lattice point here, this reciprocal lattice point reflecting one plane, contains all information what is coming from that plane. And the point is what you see then in the instrument giving you the diffraction pattern or diffraction image, this kind of points like this. This point now contains all information from a particular plane. And that is why the reciprocal lattice is used for this. There will be a little bit more on that later on, but that's the idea. This is the simplistic way of explaining what is reciprocal lattice and reciprocal lattice spacing, because it just converts planes, separation of planes, and the content of the plane into a point. And that's that. That is just mathematical description for this kind of a thing, and don't worry about it too much. Again, this is done automatically by the point. So if the system is orthorhombic, then orthogonal, then it's easy to do this conversion. But then if it's trigonal, it's not so simple. But again, it's lucky for us that the computer programs, the mathematics has been developed already. It is there. They know how to do this. And the reciprocal lattice is a convenient presentation of zero-material diffraction pattern, because each reciprocal lattice point represents possible reflection, and the vector D is often used as a scattering vector. So the actual idea of what is going in, that indicates, that contains all the information from that particular plane. Why this plane is important comes important and clear later on. So now, selection of lattice and unit cell and lattice points, and Miller indices and diffraction spot. Now in a real case. So now you got the molecule, you crystallize the molecule, and now it's ordered in 3 dimensions. And for some reason, we got a plot of information how the molecules pack. So now it's our business to devise here the unit cell, and then create the lattice plane, and then the reciprocal point for that. So the actual idea is now I selected the carbon. The carbon here is there, because if you look for this is the same molecule, but here is a different orientation, there is an orientation. But now if you look carefully, this orientation and that orientation is here, this is repeatable, and then from here to here is the same. So I connect the same orientation, smallest possible thing. So I created a unit cell. So that's now the definition. So now these atoms now, here, there, there, and there, they are in the origin. So let's consider this is origin 0, 0. That's the 0, 0 of the next unit cell, and so on. So I can draw all the unit cells now. And now each of these unit cells has the same, there are atoms missing. But anyway, if you look, this unit cell and that unit cell and that, they describe the same content, especially these ones here. And you can see that in the same unit cell, there's part of this molecule, part of this molecule, and part of this molecule, and a very tiny part of that. So it doesn't mean that the molecule has to sit completely in the unit cell, because unit cell is imaginary. It doesn't exist. Only what we have are the organized molecules. Now, let's now create a plane. So if we now add here a plane, and the Miller index of that plane is 0 and 1, we should now X-rays in there now, and the X-rays would hit. And now what they hit, they don't hit the plane because there is no plane. But there is something which is forming the plane, and what is forming the plane are atoms. So this carbon atom here and this O atom are on that plane. And now when the X-rays would hit, they actually hit the electrons of these atoms like they would be on this plane. And now when the diffraction happens, they diffract from these in there, these in there and there, and you can see they are in the same phase. They enhance each other, and they will all create now a diffraction from this point in here now, and this now creates the reflection from the Miller index plane 0 and 1. But that appears as a point. That appears like a reciprocal point. It appears a point. And now this point here, because we know the direction, we know the angle here, we know we can measure the intensity, it will tell us that in this plane there is now carbon and O atom. That's why it's important to have this Miller index plane, because in that part of the space where the diffraction happens are atoms. And then this has a value. If there would not be any atoms, there would not be any point. So that is the idea that when we see a spot, diffraction spot, it indicates that there is in this particular orientation, there is atoms. Later on you will learn, but of course it's already discussed, the electrons diffract, X-rays diffract from electrons of an atom. So there are electrons and they cause the diffraction. So the diffraction spot containing all information of all atoms situated on this Miller index plane, here O and carbon atoms. So when we record information from this plane, we see these atoms there. That's the point. This is why the diffraction happens. And this is why they have to be ordered in 3 dimensions. Now it gets a little bit more complicated, but anyway, I will go very briefly. This is just a mathematical description or visual description how the diffraction happens. And I will try to explain this. I will just open everything. So the point in there is that if you look this part here, here you see a grid. So you can see a number, and then there is 0, 0, 1, and 1, 1, 0, 1, and so on. These are the reciprocal lattice points, which describe the Miller index plane. But now the point how the diffraction itself happens, and it has been mathematically described, is that you create a sphere around your crystal. It's called a so-called evil sphere. Quite probably, if not today, tomorrow I will show you, I have a simulator program which can visualize this. But the point in there is that you can calculate around your crystal evil sphere which has the radius of 1 over lambda. So this sphere now is dependent on the wavelength. But the point there is that the diffraction will happen only when the point will coincide with the surface of the evil sphere. This is an extremely difficult, it took me 10 years myself to really understand what it means. But if I have time tomorrow or so, I will show you, I have a computer program to visualize this. And it is actually saying how technically, what the instrument have to do in order to see the information on each individual point. What this means in real life, that you have to rotate the crystal. You have to rotate the crystal that you can measure all these points which are there. But this is a very difficult concept, also my students to understand. This is just the same, I will skip it, more or less. But the point in there is that this is the reciprocal, you can also reciprocal lattice planes, but there are points. So here we're an origin, that it appears as points, individual points, and what we are doing, we are measuring the intensity of each individual these points with the instrument. But as a concept, this is because it's completely virtual, completely imaginary. It's really difficult to visualize in your head what is happening. And I will try to avoid this kind of a thing in that sense. This is just the different vectors for this. Okay, this is 1, 1, 0, and so on. And then something more is that now, if we have atoms, or let's say atoms in our unit cell, there might be a situation when there will be an overlap of these reflections. So in some cases, we will have that some of these reflections cannot occur, so they are forbidden. And this is based on some crystal systems that certain information from these reflections are forbidden. So this is an example of a cubic lattice where all the reflections, so we call this HKL reflections, this is the point from individual plane, they are all allowed, but can be 0. But then if we have an additional lattice point, so like a body-centered or face-centered, that will interfere, it will cause interference, it will kill the reflection. So it cannot occur. So in here, that's the idea in that this depicted, each of them will give a diffraction. There is no interference, but now in here, that will interfere this one here, and will actually block the reflection. So this is an information which is again inside the computer program, and it knows it. There will be a reason why this is important in the later on. Again, we are building up the house, but that is the point that it might be so that some of these HKL reflections, like this point what I'm showing to you, might be absent, completely absent. This is an additional information for us. It tells us that, okay, we don't have now a primitive lattice. We cannot select the primitive lattice. It has to be this non-primitive lattice, or the other way around. So that is an additional information for us, or the computer programs. 30 years ago, it was information to us, but now we have to do it or the computer is doing that. And this is the actual idea. This is the simple rules for this, and you don't have to memorize these. This is just for additional information. That if we have a simple cubic system, all reflections are allowed, but when we have a body-centered cube B, C, C, then this kind of a combination, H plus K plus L is odd, is not allowed. So if this is 1, 1, 1, which means 3, it doesn't exist. So that will tell us something. How do we know this? We know it from the instrument. We know it from the diffraction pattern. So because this is now an interesting thing that we develop all these things purely theoretically, which will be then shown by the actual experiment. So that makes this kind of a course very complicated, because you have to, in a sense, go through something which is virtual and becomes real in real life. But in order to understand what is going in the real life, we have to have some understanding of the theoretical aspects. But anyway, okay, that's the idea. And you can see if we have a face-centered cubic, it has a lot of these things. Here is just an example of one cubic system. So for example, this one, 1, 0, 0, is okay in here, but in these is not allowed. So if we see this reflection, we know that it cannot be this or that. So this is now programmed inside the computer programs. They know it by heart, but 30 years ago, you have to do it by hand. I did early my career, I was looking for this information. I was looking for this because the instrument will print out this information. So the idea is that systematically absent reflections make it easier to identify a particular crystal system. So it is helpful. Nowadays, computer programs are very powerful and easy to use in that sense. By the way, now I was quite fast because I wanted to go this part fast, so we have time, the discussions or whatever, because this is a very difficult, even if I would use 10 hours for this, the understanding would be very complicated. And don't worry about this too much. You can look that from the handouts. And then later on, it will come more, because we then return back to the same thing. I'm using the same terminology later on. H-scale reflection contains this and that, and so on and so on. You will then see what it actually is in real life. But this is not my brain, but anyway, this is a very important image. And I use more time on explaining this, because now, what did we do with the unit cell? We slice the unit cell into these planes, like this. And the actual idea, each of these planes contains information. And it's much more easier to understand what we were doing the whole lecture, this lecture, is that if we look a real thing. And the real thing is a human brain, a head. So can we do the same for the human head that what we did for the unit cell? Slicing and so on. And each slice contains information. And that's the case now. So the idea is that now consider that you imagine that the head here, our whole head, is the unit cell. And now what we are doing, we are then drawing this Miller index planes. We take this plane and that plane and so on. We take enough of these planes. A few is not enough, but we need tens or hundreds or thousands of these in order to reconstruct in the information what is inside these planes. And this is why I took this. So let's start from there in the lower part here, because this is the actual idea. So it starts from here, from the neck. So this is their CT scan, tomography, which is used X-rays for that. So we are doing exactly the same. We slice the head of a person. And now we start from here, so it's somewhere here in the back. So we go higher and higher. So the bigger is this thing going. So we are going more and more in here. And you can see we go from small now. Now we are reaching a certain part here in the brain. Now we are going here, here, here. Now in there, we are now approaching somewhere in the middle. Yeah? And now you start seeing that the information content of each of these slices, you can consider each of these slices like a Miller index plane. It contains information. And now you can see there now, you can see there's a lot of information now, new information appearing in these slides, which were not here. So they were in this. Now you go more and more. Now it's going up and up. You start seeing something on your forehead here. Now, this kind of a thing. And then when you go high enough, you start to seeing your eyes. So we are already on that level. So we go higher and higher. And now we can see the eyes completely here. And now we are up there. We are like going up from the brain. And now what we do exactly the same in X-ray diffraction. But we slice the unit cell, but we measure the same thing. These are the things what we are measuring, but these are the diffraction spots in the image. And later on you'll see. And what we have to do, it's the same as in here. If you join all these 35 images into one, you get a three-dimensional image of the brain. And that's the idea. But that's the point in here. Maybe this will help you to get some kind of a reference. What is the Miller index? What is the unit cell? So the unit cell is like a brain in here, repeatable, but we slice it and got information from that unit cell. And because the unit cell we can repeat in 3 dimensions as much as we can, it will describe the whole crystal. So that's how it goes. So from the X-rays, what we are doing, collecting the information in each individual slides on the unit cell, like in here, we can construct the picture inside the unit cell. And this is our structure. It's not the brain, it's not the head. And we don't use it in the same way. We are not looking for if there's a tumor or anything in here. But that's in principle the same idea. We are looking for the whole structure where the unit cell contains. And the point, that was the last line for this. So we have maybe 15 minutes time for discussions, or if you have any questions concerning this. But that was the idea in here, to try to visualize the very complex, mathematically very complex thing, which is purely imaginary. But then the lucky thing for us is that when we do the work in the real instrument, the instrument will tell us things. We don't have to know all of these by heart, but it's actually the idea of why do we collect this? Why this is important? And that's the actual idea, why it's important to collect as much information from the crystal as possible, and why it has to be 3-dimensionally ordered. We can't do this if there is no order, because there is no diffraction. Diffraction only happens when there is an order. So there's always, this cannot happen if this is not true, and so on and so on. But if you have any questions, so please ask now, or you can ask whenever you see me. So that's the idea. But I think tomorrow I will then try to visualize this in the next lecture about with the simulator. And the program is, by the way, such that if you like to have it, you can have it also. And it runs on Windows, but we will see that later. Okay, I am happy. If you are happy, then.
Any questions? Anyone?
One, yes.
Apart from that simple cubic and body centered and face centered, one term arises like that edge centered.
Yes.
Edge centered.
Yes.
But after that, you have not mentioned that edge centered any of the crystal system.
So the idea is that this A-centered is non-standard. It's not forbidden, but you always try to select the unit cell that it would be C-centered. But in some cases, that depends on the system. In computer, if you have used this, the idea is comes from there that because always the computer programs are designed so that they want to have the angle, this normally is a triclinic monoclinic system, they want to have a beta angle as close to 90 as possible. Then it might be that the A-centered has a beta angle closer to 90, and then it's there. But then you just have to select it. But that's absolutely, as I said, you can select it anywhere like you like, but it's on convention we use the C-centered. It also could be B.
Okay.
That's the case.
Thank you.
Okay,
Thank you,
you're welcome.
So anyone?
Okay.
Sir, sir, sorry, I apologize that my question is from your last lecture, I mean second lecture.
Yes.
Sir, we saw that total 7 Brevis lattice are
Yes.
there.
Yes.
And total 14 primitive
Private
and
lattice.
non-primitive
Yes.
lattice
Yes.
are there.
Yeah.
But all Brevis lattice are not showing BCC or FCC. Some are showing BCC or some are showing BCC means body center cubic.
Yes.
Sorry,
Yes.
sorry,
So
sir.
that's the idea. So
Yeah.
that is there are only 14 possibilities
Yeah.
because if you make more, they overlap. So it has been agreed some IUC are 100 years ago what to use as a standard.
Yeah.
But as I pointed you out, you can select whatever. So there is other combinations are also possible, but this is agreement. So that's the idea. It's 7 crystal lattices and 7 other ways how to combine them to 14. And that's the idea.
Okay, okay. Thank you,
You're
sir.
welcome.
Anyone? Yeah.
Okay, yes, yes.
So actually okay. So when X-ray is falling on the crystal,
yes.
So can you give a detailed insight of that how the interaction is happening with the electron of the crystal, that molecule forming the crystal?
Yeah.
The X-ray is falling on some of the atom of that molecule. So how the interaction is happening?
So that we will discuss. We will actually, I think, discuss that in the next lecture. In that sense, that what is the interaction between the electron clouds, electrons, and how they interact, how particle atoms interact with the X-rays, because each individual atom interacts with the X-rays differently.
Yes.
And that will help us also say that which kind of atom we have. But the idea is the interaction with the electrons is always the same. It is really that it has a tendency to diffract. You can consider the electrons of an atom like a mirror or something like this. And then the more electrons you have, the bigger is the mirror. So the more electrons, will diffract more. And this is how different atoms interact with X-rays in the crystal.
Okay.
That's how it's done.
Thanks.
Okay. Okay.
Sir, I am saying that you have mentioned that the hexagonal systems have a trigonal part in it inside it.
Yes.
And you have also mentioned that the orthorhombic or no, rhombohedral.
Rhombohedral, yes.
Rhombohedral and trigonal
Yes.
systems are the same.
Yes.
So it can be, can be concluded that the hexagonal systems have the trigonal always.
Yeah, they have. So the idea is now that the trigonal system is unique by itself, because trigonal system cannot contain six-fold symmetry, but the six-fold symmetry can contain three-fold symmetry. But then the hexagonal system can be described as rhombohedral system, but looks like a trigonal. But that's the idea. So this is kind of a conversion in that sense, and that's why it's called R definition, because you will learn about the symmetry inside the unit cells. And when we have a rhombohedral system, then the definition is not anymore P or C or so, it's called R. And that's the idea. So trigonal symmetry, threefold symmetry is unique by itself, but hexagonal symmetry contains this. Okay. It's the idea, of course, if you have a six-fold symmetry, you can rotate it to only one half and then it's threefold. That's the idea.
And so another question from the last lecture is that you have mentioned the Miller indices, and from the Miller indices we are getting the the X-rays is falling, and we're getting the data, some XRD data, let's assume. Yes. So the data we are getting, if we are getting one data for the one Miller indices, or we are getting
one.
That's the
it's always one. So one Miller index is one information. Okay. But this one information contains all information from that plane. So that we will learn later on, we call so-called structure factor, which contains all the information about all things happening in that plane. And that's why I was using the brain scan, that individual scans will not show everything. They show part of it. And it's the same with the Miller index. It contains part of the information from the whole structure. And if you record, for example, 50% of the Miller indices and leave the other 50 unmeasured, you will not be able to solve the structure because you don't see it. So that's the idea. You need the whole information. And that's the point. So it was a good question that there is a one number, but this one number contains all the information on that part of the space. So you have to, in a sense, sum up all of them to get the full picture.
And one last question.
Yes, please.
Sir. And I have done some, made some crystals and see the XRD data. So I have one question, that the number of peaks we are getting, that is the number of Miller indices in that crystal.
Yes. So if you do a powder diffraction, each peak in the powder indicates one Miller index.
Okay.
That's the idea. And that's why the powder diffraction doesn't give you the structure in a very few cases, because you might have 10 or 15 or 20 or 50 lines. But in a single crystal X-ray diffraction, you might need 10,000. So that's the idea. And then in single crystal X-ray diffraction, they appear a spot, one spot. But in the XPD or powder diffraction, it's a line. It's like a pattern. And that's the idea. But they all are Miller index things. You're absolutely correct.
Can we specify that peaks, that these peaks is that Miller
index? Yes. But then you have to know the unit cell.
Okay.
It can be done. So then you know the unit cell, you can say this peak is 20 or whatever. It can be done. Okay. Normally, then in the powder diffraction, it's given by the angle. So the peak appears in 10.5 and so on. But each individual peak is the information from that Miller index.
Thank you, sir.
Very good question, yes.
Anyone?
So you are warming up. So that's nice that you can ask questions.
Okay,
but anyway.
Sir, I myself have one question.
Yes, please.
Actually, in the eval sphere, we are actually taking, after that, we are taking a Fourier transform, inverse Fourier transform. So the space where we are taking, we are considering the distance metric to be Euclidean metric.
Yes.
So my question was like, what if we use Manhattan metric or maybe any other metric? What information can we actually get?
Actually, we will not get any other information, because there is just mathematical transformation. So it doesn't change the actual data. So it doesn't. The content is not there. So that is the X-ray diffraction is that sense different, that all the information is concentrated on this diffraction spot. So for it depends on, you can consider that's a Miller index or the diffraction spot, how it's been done. But the point in there is that based on the diffraction, well, the Ewald's sphere or the diffraction law, the diffraction happens only on certain conditions. And this is really what I said, that when the reciprocal lattice point it coincides with the Ewald sphere surface. But it doesn't change, you can calculate it mathematically, the precision and everything, but it doesn't tell anything about the intensity.
Yeah.
So the intensity contains all the information. And that's the idea. So that's the idea. But there is a Fourier transform comes afterwards. I will show you. Yeah. Yes, because I will show you then in a talk what the Fourier transform means for a diffraction image. So the diffraction image is correlated to the structure through Fourier transform. Sure. But it's just the information in there, and we have to extract it out.
But all the information based on the Euclidean metric, that's the maximum amount of information we can extract.
Yes.
Based on okay.
Yes.
Okay. Any other metric will give lesser amount of information.
Yes.
Okay, sir. Thank you. Anyone here? Any questions? Curious minds? Okay.
Okay.
Okay, guys, let's have a round of applause for Professor.
Thank you.
So there's a small announcement. Please, everyone here are requested to just stay like for a few more minutes because our director will be coming here for another part of the session. So yeah, that's all.